Okay. Hi, everybody. In this lecture, I am going to discuss with you two interesting objective functions. One of them has a global minimum and a local minimum, and we have to define them. We shall do that by using Python and by using LabVIEW. The other objective function is what is called Rosenbrock function, which is a standard function which exists in the library of LabVIEW and in the library of SciPy. This is considered a test function, very often used in machine learning in order to test the worked out algorithms. So we begin with the first one. The first objective function, as you see, is x squared plus 2 multiplied by np dot sine x np dot pi. Remember, when we say np, this is a shortened form for numpy. We have imported numpy as np here. And numpy includes the constant pi, and also when we work with trigonometric functions, we use numpy functions. We write np dot sine or np dot cosine and so on. So this is the expression of the objective function. As you see, it includes a sine, so it will have a somehow wavy form. The name of the function is func, and its variable is x. X in this case is an array. It is created, as you see here, by np.arrange, which begins the limits of this array from -2 to 2 with intervals or steps equal to 0.05. This is the array which represents the values of the x-axis. Function f of x is assigned to a new variable called y, so that we can plot the function y as a function of x. So when we plot it, we write plot function, and we pass there the two arrays. The first one, which is the array of x-axis array, and the other one is the values of the function y, because each value of y corresponds to a value of x. We include there a grid. We write plt grid function. The plot will include a grid, and we ask matplot library, matplotlib, to show the function. The function, as a result of this, will be like this. As you see, it has the first minimum. This is the global minimum, and this is the local minimum. Now we shall try to find the global minimum. Already is found, and I'll show you how. And then we will find also the local minimum by using Python. To find the global minimum, it is sufficient to work with the minimize scalar function, which is a function of SciPy. From the optimize function out library of SciPy, from SciPy we import optimize, and from optimize we import minimize scalar function. This scalar function is sufficient to detect the global minimum, but it cannot detect at the same time the global minimum and the local minimum. So especially I introduced it here so that we will see how we can get it, and then we shall try to find the local minimum. So as you see, as a program, we have imported at the beginning the necessary libraries as SciPy in general and the optimize module. And from the optimize, we imported the minimize scalar. And we also imported matplotlib and shortened it as PLT as usual. And we imported NumPy also library. Now we have defined the objective function as func, as I told you, and we have created the array x, which represents the values of the x-axis, and also now we established y from here as a function of x, so we can plot now the plot of xy. So when we run this program directly, we will get, as you see, what we shall see from as a result of that, we take minimize scalar function and pass there the value so that it works. This scalar function, we pass into this scalar, minimum scalar, the function itself, which is called func. We write here func, and we select method of print. And now we print the result. This is called a result variable. We print the result, and from the result exactly we want the coordinate x. Print result dot x, the value of x. Also here we find the value of the function for, or specifically for the value at minimum, which is the result dot x. Now, in order to plot this dot here and to show the minimum value where it occurs, so we need to know the coordinate of the x at this value, which is already now known because we asked the program to show the result dot x. This is the result dot x, and the function of this value gives us the ordinate or the y value of the minimum of the function. We shall show it as asterisk here with a red color, as it is shown here with a red color. Of course, you can change as you want. You can change it to a circle, for example, or you can change the color to any other color. So what do we get from the result? That the process has been carried out successfully. Success, yes, true. And the value of the function is minus 1.77. And the coordinate x where the optimum occurs, 0.45. If you look at here, you will see this is 0.5. Here is 0. We are moving towards minus 0.45, where it is. Yes, here, minus 0.45, it is in minus. So we are from 0 going downwards up to this point here. This is the value of minus 0.45. And the value of here it is on this axis. And the value which corresponds to this x value is the value of the function, which is here minus 1, here minus 2. It is in between, it is minus 1.77. Minus 1.77. So as you see, it's okay, normal. As you see here, I myself asked the program to print the result and to print the value of x taken from the result. But indeed, when you write here result, you can get this information from the program directly, and you need not to repeat yourself. So here you find from the result, as a general, you get the coordinate of the value x, which is 0.45, and the value of the function at this specific point, which is minus 0.177. Of course, you find that they are the same values which we can get here, result x, and the function of the result is here. So we have them twice, as you see. Okay, well, this is not bad. Now, what we do in order to find the local minimum here. To find the local minimum, we shall use another function which uses constraints or bounds of the variable x. It is called f minimum bound, f min bound. This function belongs also to SciPy. So we at first have to define the range where we expect to find this minimum. We already know this function here. We see it. And as you see, the minimum is in this point. So it is in this range between 1 and 1, maybe 0.5. We can take any value to the right and to the left of this point. Of course, if it is taken as 1 and 1.5, it will work and there is no problem. So at first, we need to define this maximum and minimum values. X minimum is equal to 1, and X maximum is equal to 1.5. Now I shall include them to the program. I shall cancel this hash sign, and I will call from the optimized function f min bound. This is the function between brackets, and pass there the arguments, which is the function itself, and the minimum and maximum values, which are here defined. So now I can include it to the program in order to get the x minimum, the minimum value of the coordinate x. Yes, I want to print it. Okay, I print x minimum. I also exclude the hash. And now I want to plot it. I call the plot function, as you see, plot scatter, and include there the minimum value and the ordinate or the y value for this x minimum, function of x minimum. So I will plot two values only, not arrays, two values, the x minimum value and the function for this x minimum value. This is plotting, so it will appear now. Also, I can print it and see it as a value and how much it is. Now the program is complete. If I run the program, I shall get here the minimum point already overlaid on the function, and its value will be about 1 here, 1.5 here, 1 dot, maybe about 3 to 4. Exactly, it is equal 1.3577. This is the value of the x coordinate of the local minimum. And if we want to find the value, this is the value of x. If we want to find the value of the function, which is print x minimum, I called it local minimum, print local minimum, which is a function of x minimum. Local minimum is here. It is dot 0.39. If we go, it is about 0 value. If we go here is the 0 value, and really it is about a 0 value, a little bit moved upwards. It is positive, up a little bit. As you see, this is the value. So as you see here, we can manage and we can define the global minimum and the local minimum separately by using the optimize function with the other functions which exist within it. Okay, now we have finished with this example. I want to show you how we can solve it by using LabVIEW. So I shall go to the example 8. I have a folder for LabVIEW examples. This is the folder called optimization in LabVIEW. And here is my function. It is given a name. I think it is, let me see, 811 or 812, I am not sure of it, but it will be seen. If it is not the case, we can move to the other program. I think it is not our case, but I have already opened it. Let us see what it is. No, it is not our problem here. So I go out of it and open this. This is our case. It's not seen. Okay, now I enlarged and you will see it. So what I have done in order to find that, let us have a look at the program, and when it is necessary, I will refer to the front panel. Here is the program. This is the function which exists in LabVIEW. It is called find all minima one-dimensional.vi. To find where it is, I right-click on the block diagram and go to the mathematics, to the optimization, and here I will find it. Here, this is the VI, which is called find all minima 1D VI. Of course, as you know, if I press it and put it on the block diagram, it will be the same as here. Okay, so I have this function, and I will, of course, to know about this function, as you know, you can go to help and see a little, I can say, a sufficient information about it and for what purpose it is used. It determines all local minima of a given function in a given interval. So in order for this function to work, you need to supply it from the left side here, the input values, and to the right side, you can get the results. Here you need to input a start point and an end point. What does it mean? Here is written. Start is the start point of the interval where we are going to look for the minimum value. And end, of course, is the end point of this interval. The initially, or the default for the start point is 0 and for the end point is 1, but this could be changed upon request. Formula, this in pink, represents the function which we are going to minimize. So if I go here, this is the function, here is the formula. I right-click it, and select create control. Here is a control now. And this control will be from this side, you will connect it to this point. And on the front panel, you will have a reference for it here, where you will write the function of interest. The function of interest is here. It is called, as you see, x squared, which is the same, which was with Python. X squared plus 2 multiplied by sine pi x. Note here that we are not required to use NPy. You use it in the normal way as we do in any mathematical expression, which is really an advantage for LabVIEW. So it is x squared plus 2 multiplied by sine 3 pi, which is pi, multiplied by x. This is the asterisk, means multiply. Now, in order to draw this function, x here is, as I told you, it is an array. It is a series of values. It represents the x-axis. So I have tried on my own to create an array here with values beginning from -2 to 2. This is the same I did as with the Python example, between -2 to 2. The interval I took here, as you see, 0.25. 0.25, adding for each step here, 0.25, here minus 1.25. Now I add 0.25, it becomes -1. I add 0.25, it becomes -0.75, and so on. When I run the program, I have got this expression, this figure here. As you see, it is a distorted form. It is not trimmed as should be. Why? This is because the number of values which I have taken here is very limited. The interval 0.25 is large enough. I have to include here more intermediate values so that to give or to get a fine figure as it is here, for example. For the program to work, really, I tried it and it worked well, and I have got the same answers by using only this figure. But generally speaking, this is not the standard case. This figure must be drawn as a complete without these distortions at different points here. So how to do that? This is which I am going to show you. So this is, as I told you at the beginning, the program itself. This is the input, which is the starting point, -2. This is the ending point, which is 2. Here I selected, you have the option here to select modified function or fixed function. I have selected the fixed function. And the print with derivative or print without derivative, with derivative, or golden section search. I selected print with derivative. And this value here represents the tolerance or the allowed error for the program to work. Now, in order to draw the figure, of course, I have, as I told you at first, generated the array X. This X is the same X as is here. This is the X array, or array which represents the X values, and its terminal is here, this block, and you see inside it there is 2 brackets which denote that this is an array. And I multiplied it. Here it is X multiplied by pi. So this is pi. How to get pi in Python? Not difficult. You go to the numerics, and there you find mathematical constants, and there I think it is there. You can find, yeah, here it is. Here is pi. 2 pi, pi divided by 2, and so on. So I have multiplied the array by pi at first here, as it is in the expression here. Then I will find the sign of it. Now it is passed to the sign function. The sign function also exists in the mathematics. You go to the elementary functions, trigonometric functions. Here is the sign function. So it is passed to the sign function in order to get as the output the value of the sign of this expression. But this value must be multiplied by 2, so I have multiplied it by 2 with this 2. The output here will be added to x squared. X is the array again. So this is x here. I have squared x. How I square it? You go to the numerics, and there you find a function called squared, where it is here square, as you see. So I squared the x, the array, and then added here as it is squared, and then added it to the term which I have already designed here. And at the output now I'll get the objective function. So here I have the objective function as an array. As you see here, small brackets denote that this is an array. And you may not look at it. You can just look at the line itself. The thickness of the line shows you that this is an array. If you compare this line with this line, this is a value, thin line. This is a thicker line, which shows that this is an array. So this is the array of the y, and this is the array of x. Now I have to bundle them together and show them in the xy graph, and they gave me this figure here. So this figure now we know how it appeared and how it comes. What to do in order to avoid the distortions which happen to the curve? Of course, logically, I told you I can increase the points here in the x, but suppose that this array has 500 or 100 or 200 points. To add them by hand, really it is a tedious work and it is not logical. So there should be more interesting ways to do that. I am showing one of these ways here to make use of Chebyshev approximate function, where it is and what it does. Here you see the input is -2. I put specially as an input start -2 and an output as 2. And this Chebyshev approximate represents, in general, as you see, a multi-term function, polynomial function with a given order. And this order here is adjustable. You can give the order you want. Now, the number of points which you want in this polynomial depends on you. I have put 50 points, and I found them sufficient, really. I can increase them now and show you how it will be. And at the output now, I shall get an array for the value of x and one other array for the value of y. And why the value of y appeared here? Because another input to the Chebyshev approximation is here. I introduced the same function which I introduced to find all minima 1D. So the function is given here. The number of the points of the function are given here. The limit values of the function are given here. And this order is only given to trim to make the output finer and finer. First of all, where to find this Chebyshev approximate function? You go, let me cancel this one. I go to the mathematics and go to scripts and formulas. And I think to calculus. No? Not there. So again, by repetition, one can remember it. Script and formula to calculus, you go. No, not to calculus. Again, I know it is in the mathematics. Where it is. Anyhow, if suppose that I have forgotten where to find it, what can I do? I can at the same time go to the help. Now it appears here. Here, Chebyshev approximation VI. The Owing palette is called optimization VIs. So I have to go to the optimization VIs. There I find it. So to find it is not that difficult, as you see. And I have to go to the block diagram and to the optimization as I have seen there. And here you find the function, Chebyshev function. If I press it and put it here, it will be exactly the same as this one here. So no problem. We have found it. Now it is existing. We have furnished all the requirements for this function to work, and we have got at the output the array of x values and the array of y values. And as we did above here, we bundled them in order to show them in the graph. Now we shall have another graph. This one is called XY graph. This one is called XY graph 3. Here it is. This one is called XY graph 3. Now look how the shape is here. Now concerning the result. This function, as you see, at the same time, at the same moment, finds for you all the minimum, find all minimum. So you have two minimum values of, these are the coordinates of x. One is minus 0.45, you remember this. And the other is 1.36. Here, the first one here, as I showed you, this is minus 0.45. It is a little bit shifted to the right. And the other one here is about 1.5. It is not 1.5, it is 1.36 exactly. Here, it is very difficult to judge where it is, but although you can, by the inclination of this line, guess that it is coming to this direction, and it is about 1.3 or like that. Exactly, it is 1.36, and here minus 0.45. These are the coordinate x values, and at the same time, you get the y, which corresponds to this value, which is minus 1.77, and y, which corresponds to this value, which was about 0. Here it is about 0. Here it is, if this is the function 0, it is about 0, but not 0, of course. But if you compare the results, they are the same. This is how we can work with LabVIEW in order, by using find all minima 1 dvi, in order to find the minimum value of the x coordinates here, 2 x's, and the y value at the same time. Let us also consider, I have finished with it, I don't save anything. This is not required. I want to show you also another example related to this issue here, which is given a number close to the 811, 812, 8122, I called it, so that to remember it. So here is the program. And what is there? It is the same thing, except with some changes. Here is the program which I made for you. I have told you that at the same beginning, I need to create an array of x values which represent the x-axis. This code alone gives an array as the output, which represents x-axis. Here is x-axis. Here I have tried to see the size of this array. How many elements are there? The elements are equal to 0 because I didn't run the program. If I run the program, there are 82 elements. Not 50 as I did before, there are 82. The figure itself, as you see, is completely very nice and exact. Here the point is at 0 practically, and here is the point at 0.45 or minus 1.77. The same coordinates which I have got before are existing here. What else? What is this array for? Let me go and remember what I have done. This piece of code, you remember it, I have introduced to this code the value of x taken from the x array which I created by hand. Instead of putting that array now, I connected this array directly to this figure here. And now as the output here, this is the output now. I look at the pointer, I took it here, this is y, and this is x, the same value of x, bundled together here. Now if I connect here x and y, I shall have the same figure at the output. but I want to fix the minimum point on the figure here. This point, I want to fix it on the figure to overlay it here. When I run the program, it will not appear alone. So I have managed so that I can put it there. So what we have done here, first of all, let me tell you, this is the Y output. There is a function in LabVIEW called array maximum and minimum, and now I can get the minimum value if I want. Here it is again minus 177. So no problem. This is very good. This emphasizes that we are getting exact answer. This is just to show you also the size of the array Y. It will be very similar to that of the array 3. It is called, here it is 82, and here it is 82. The same size. No problem. That is good also. What else? Now we have taken as the output here, as I told you, the data which represents the plot. But I didn't connect XY to it. I want to, first of all, create an array here. This is build array function. I can have it from here, from the array build array. This is the build array function, and when you expand it, you will have this figure. I have a build array of two clusters. This cluster, which includes the information of the function, and this cluster now, which includes the information related to the point which is going to be overlaid on the plot. So here and here are values which represent the point of interest. Let me show you this point here. The X point, which is minus 0.45, and the Y point, which is minus 177. But these are points, and if you want to draw, you need to have an array. If I go there again and show you in the block diagram, here is I have shown you an array coordinate of X. Here is an array coordinate of Y. How it comes? No problem. The X value, now I go there back. The X value here is created not as a constant, but as an array. How I did it? Okay, I go to the data containers. This is the array. This is the container of the array. I go to the numeric and I take a constant control. And now the value which is here will be minus 0.045. This value now is an array, but only with one value, which will be included in that figure here. So this is the array, but this is the array of one value. And this is the other array which includes the value of minus 177. Now these two arrays with one point, xy, now are made as a unified array, which means that they are included with the figure here. And now this figure includes this point. If I disconnect it, it will not be seen. If let me move this one a little bit for what does this array for me? It seems it is not necessary. Okay, let me finish with it. It is not necessary. If I disconnect this. This means there is an error. So I have to collapse it. And now it is okay now here. He is telling me that there is a problem. Show the error. Yes, the error is related to this part of the program. This is not necessary for me at all. I just wanted to explain to you. Anyhow, let me finish with it. And all this part, I can finish with it now and work with it again with you. Okay, these are taken away. Now the program is okay. Now, as you see, the output here is given to an array with one element, and the block diagram here, you see there is a point. This point really, which was before. Now, if I run the program, it will not appear. It has gone. No point. I cannot show the point where the minimum happened. So I need, as I told you, to join through this array the output of this point with it. Now a new array arised, is real, and if I run the program now, I shall have the point there. Here it is now appearing there. So I think this is useful to you. Now what I have done, suppose you are working instead of me and you need the information here which has been dropped out. All what you have to do is to go out, exit. It will ask you save or don't save. I say don't save. And now everything is in the same place. I go back and open it. It will be back. Now I go to the block diagram. You will see it completely back. What I have done here, I really have done some explanation, not more for you. I wanted to tell you that this pink lines represent in LabVIEW clusters and include a lot of information related, of course, to definite parts of the program. So I have taken this cluster and converted it from array to cluster. It is now the output array. This is the array. I converted it to cluster. And now, by using unbundle by name, I found here two values or two names to be given 0 and 1. One of them represents the X data and one of them represents the Y data. Not more. The same thing with the first element here. X coordinate or Y coordinate, just to show you that what they're inside, not more. But it is not that important for the program. So again, summarizing for you this program here. So what I have done, I have created at first an array X programmatically and fed it to this part of the program where we created the objective function. And this is the output Y of the objective function. And this is the output of the X, which represents the range or the array of values of X. And now I can use them to directly plot the figure. Again, let me show you. Maybe you are, this is the front panel, for example. I create at the front panel another graph. XY graph. And now this XY graph will appear here. Here it is. I take it here, for example, and connect it with this. And now I shall have only the objective function. If I run the program now, you will see it, but you will see it without a point. Now, I hope that this is understandable. Okay, let me show you one more interesting thing. File, exit, don't save. Let me show you another modification of this program. It seems that the lecture became long in time, and I think that it is better to leave the Rosenbrook function for another specific lecture. So this is the, sorry, here is the figures which I have got. Here is the minimum minus 0.45. Here is the, this is for the X values, minus 0.45. And this is 136. Here it is, this value. Here if you come back here, 136 here. Okay. And this is the value of the function here, minus 177. And this is the value here is above 0. Minus, I see, 0.04. So what is there? What is here? Nothing new, as you see. What is there? Okay. Remember, when I created the objective function, I used the function which is given as a mathematical expression and convert it or build it newly by using the basic elements in LabVIEW. Here we can use the same function y, which is the objective function. Y is equal to x squared plus 2 multiplied by sine pi by x as a formula. And we put this formula here inside what is called the formula node in LabVIEW. This is maybe easier. You do not need to build from the scratch, especially when this function is complicated. Maybe it takes a longer time to build it, comparable with this case. So, okay, I have written the objective function inside the formula node. Now this x is an array. So I need to pass here an array of values of x. Here is x, which I built in the previous example. This is the array. I took the array and input it to a for loop. Now, as you see here, this is the indexing tunnel. It asks you disable indexing or not, or keep indexing. I kept indexing. What does it mean? The array here, which comes with a set of values, now is entered to the formula node one value after another. This is one value, and then another value. And the interval of time is decided, of course, by the operating system, or you can include here a timer as you want. If you want the process to be taken a little bit slow, for example, 1000 millisecond, 1 second. So now every 1 second, one number from this array is given to the formula, and one y here is calculated. At the output here, you will get this y calculated, and the result of all the y's which are calculated are gathered here as a new array. So at the output here, I will have a Y array also, which corresponds to the X values of the input. And now I bundle it as I did before with the X value here and show it through XY graph 2. This is the graph which arises now. If I run the program now, I shall have this figure as it is. As you see, doesn't change because it will not change. So now I have shown you how this happens. This part of the program is the part which was before. This is the part through which I created Y. Instead of putting it here as a formula, I have created it here, and this is the output which represents Y. And this is the X, and they are concatenated, and this is now XY. So this and this one must be equal. They must give me the same result, these two things. If I wanted to test that, are they different? If I take this output and this output through an array, and I show them on XY graph 3 here, you see, I can see only one graph. Why? Because this graph is 100% the same as this graph, and they are overlaid on each other. So you cannot see the difference between them. This is a test I have done specially to see that they are exactly 100 the same. What is this here then? This is the last issue which I want to tell you. In LabVIEW, there is an interesting, very interesting also, function called evaluation of Y equal function of X. As the output, you get two arrays directly. One of them represents Y, and one of them represents array of X's. And if you have this array of X's and this array of Y's, and you can bundle them together, this is a bundle function, you will get the same figure. But this is happening only if you have the same limit. So I took here, this function requires from you the start input, which is -2, the end, which is 2, the function, which is the same function, I have added the same function, and then I have got at the output the two functions, the two arrays, which represent the X and the Y values, and then as a result of that, I can bundle them and draw the output here. So as you see here, I have drawn the function with 3 different ways. Completely 3. One of the ways by using the X array and by using the model of the objective function. The other way is to use the X array and to use the formula node. And the third way is to use the evaluation of eval Y equal function of X. Where this function come from? Here, okay, the problem, it is stopped. If I go to mathematics and I go to scripts, I think it will be with the calculus here. No? Again, so I want to go to the, I think, logically to the optimization. Maybe, no, I don't think it is in the optimization. Scripts, calculus here. No, it is not with the calculus, it is where then? Let me go out of it. And you will go to the mathematics and then go to the scripts. and then go to the calculus. Not there. Okay, I have forgotten. So again, I can go back here to the help and see where it lies, where it is included with. It is owing palette one-dimensional and two-dimensional evaluation VIs. 1D and 2D evaluation VIs. Where it is, owing palette, 1D, 2D evaluation VIs. Okay, let us see there. So again, I go here to the optimization, mathematics. Here is there 1D, 2D. I cannot see any 1D, 2D evaluation VIs. And the scripts, here it is, 1D and 2D evaluation. And I put the cursor here. Now a new palette opens here. In this new palette, you find our function here, eval y equal function of x dot vi. If you don't know about it, of course, as a beginner, why not? This may happen. You just take it and put it here, and then go to the help and read about it. It shows you, it gives you that it calculates the values of one-dimensional function. So, okay, you have to, of course, the function should be included, which is this formula here, given by a formula at equidistant points in an interval. Okay, and in an interval, which means between the start and the end or the stop intervals, and number of points you define yourself. I have defined there the number of points as I think 50 or like that. I don't know, 100. I have taken 100 points. But here it was 82 and here it is 100. It makes no difference, really. You cannot see that this function is smoother or more smoother than this function. They are exactly the same because the range of 100 or 80 or 75 is normal for this function to be drawn normally. So as you see, this world is very interesting. We have a lot of information today, and many varieties. I have shown you how to create equidistant array representing the x-axis, how to realize or to make use of the objective function, either by plotting it by using elementary functions or by using the formula node. And I think with this, let us finish our lecture today. And I promise you tomorrow we shall work with the Rosenbrock function, also with a good detailed information. Okay, thank you for listening and wishing you the best. Goodbye.